So we want to talk about sending action potentials and communicating between neurons. But action potentials are just this wave of electrical currents going down the axons of these neurons and changing the membrane potential in a certain way that transmits a message, right? But to get there and really understand action potentials, we should really know a bit more about membrane potentials. So there are two things that you need to know about membrane potentials. First of all, they're determined by the uneven ion distribution across the membrane, as well as the membrane permeability to those ions. So this is our beautifully drawn neuron over here, and you have these ions are not distributed evenly across the outside and or the extracellular space, and then the inside or the intracellular fluid. So you can see there's a lot more potassium within the cell, and then there's a lot more sodium, chloride, and calcium outside the cell. So this different concentration of ions creates a chemical gradient, right? Because the ions always want to move from high to low concentrations, right? So in this case, the potassium, which is in a high concentration within the cell, wants to move down its concentration gradient and get out of the cell. And on the other hand, you have sodium, which is in a high concentration outside the cell, and it wants to move down its concentration gradient and come into the cell. So when we're looking at individual ions, there's a specific equation that we can use that will help us determine where they want to move. So if we're looking at the ion distribution across the cell membrane, we can use the Nernst equation. Now, something really important to know about the Nernst equation is that it only looks at one ion at a time. So you could look at sodium by itself or potassium by itself, but you can't look at them both at the same time. So what it does is it calculates the equilibrium potential of an ion, and equilibrium potential just means what the membrane potential of the cell would be if that membrane was permeable to that ion and would let it continue to diffuse and move across as much as it needed to until it reached that equilibrium state, during which it would be like at equal concentrations within and without the cell. For example, if you look at potassium, it's in a higher concentration within the cell, right? But if the cell membrane somehow just let all that potassium diffuse across and then balance out through both sides, the membrane potential of that cell would become negative 90 millivolts. But then if you look at sodium instead, and you have all that sodium is allowed to diffuse in and then even out, reach that equilibrium state, the equilibrium potential or the membrane potential of that cell would become positive 60 millivolts. Now, when we compare these equilibrium potentials with the actual membrane potentials of that cell, we can learn a couple of interesting things. So first of all, the resting membrane potential of a neuron is usually negative 70 millivolts. So that's because you have a lot more positive ions in a higher concentration outside the cell, and then you have less of the positive ions concentrated within the cell. So more positive on the outside means you're less positive on the inside, or more negative. There's also those negative charges actually come from like the phosphates all over your DNA and like ATP and all that good stuff. But in general, it's negative 70 millivolts in a resting cell membrane. But it's not negative 90 or positive 60. So when you're comparing this, when we're using this Nernst equation, it's important to remember that this only looks at the distribution of ions, the different concentrations within and without the cell. And it's only looking at that one ion. We have to look at all of the ions. So if you want to combine them, okay, can I just say like it should be between positive 60 for like your sodium and then negative 90 for potassium? Well, no, because I mean, first of all, you have to consider all of the other ions that are coming into play, and you also have to consider the relative permeability of that membrane to each of those ions. So neuron cell membranes, for example, are more permeable to potassium than they are to sodium. So that means that potassium can pass through more easily, and therefore will have the the resting membrane potential is going to be closer to the equilibrium potential of potassium than it would be to that of sodium. Um, Fun fact about equilibrium potential. So if you look at the sign on whatever your equilibrium potential is for that ion, you can figure out which way the ion wants to move. So say I would, like, you didn't have this picture and you didn't know if the higher concentration of, say, potassium was inside or outside the cell. And I told you, well, the equilibrium potential of potassium is negative 90 millivolts. So since it is negative, that tells you that it wants to move outside the cell. But if I gave you the equilibrium potential of sodium, which is positive 60 millivolts, that positive sign tells you that sodium wants to move into the cell. And after that, the magnitude of that number would tell you like how much, like if it really, really wants to, or if it just like kind of wants to move across the membrane. But yeah, so that's what you can use the Nernst equation for. But now when you actually want to calculate membrane potential, you use something called the Goldman equation. So the Goldman equation is pretty much just like the new and improved version of the Nernst equation. So Nernst equation, you looked at, the different concentrations of one specific ion inside and outside the cell, which, it's good. You got that ion distribution part, which helped you, calculate equilibrium potential. But if you want to calculate the actual membrane potential, you have to use the Goldman equation because, first of all, it looks at not just that one ion and its distribution, but all of the different ions that the cell is permeable to. So, say you have a cell, in this equation, there's no calcium, so that means that the cell in this case is not permeable to calcium. So I don't care if there is a concentration gradient, and calcium would want to move inside the cell. If the membrane is not permeable to it, it's not going to allow it to get through, and therefore it will not affect membrane potential. So calcium, sorry, you're not going to get to be in this particular Goldman equation. So Goldman equation looks at many different ions, all the ones that have an impact, and then it also takes into consideration the relative permeability of each of those ions. So in this case, you would have the permeability for potassium would be larger than that for sodium, which is why when you get the resting membrane potential and you calculate it properly using the Goldman equation, you get negative 70 millivolts, which is closer to the equilibrium potential that we calculated for potassium from the Nernst equation than it is for that of sodium. Because if you take that, it's the resting membrane potential, even if we're only looking at these two ions, is not going to be perfectly in between those two, but you also you would give more weight to the equilibrium potential that you got from potassium because the cell is going to allow a lot more potassium to get through, and therefore the membrane potential of the cell will be closer to what it would have been if it were fully permeable to just potassium and less permeable to sodium.